Okay, what I'd like to do is talk a little bit about some work I've done recently combining what I call real-time with long-time. So if there's anything that real-time systems do, it's generally gain speed by giving up persistence. They keep things in memory and stuff like that so that they can go really fast. But if you want to store data for a long time, that sucks. Likewise, systems that typically store data for a long time don't tend to go as fast because they're persisting it. And so there's this gap. And so what I want to talk about is a way of filling that gap. And in particular, I'm going to talk tonight about a version of Hadoop, which is great for storing great vats of data for a long time, but it sucks by design for real time. And that's why Hadoop is fast, is because it sucks. It was designed that way, taking trade-offs in order to meet its primary mission. Storm is great for real-time processing, but it lacks any inherent way to do batch processing or really large amounts of data. So it sounds like the, kind of out of luck, but it's not really a problem. It's an opportunity, as they say. So here's a picture of the problem. So we got time. Time is always an arrow. Metaphorical lack of imagination, or lack of metaphorical imagination. Here is the latest full period of data. And the Hadoop job is going to take a little bit of time after the end of that full period of time to do a batch processing of it. Unfortunately, right there is now. So the Hadoop thing is not done. So inherently, Hadoop can cover this stuff, the green stuff, and it can't cover the red stuff. So that's how close to real-time Hadoop is. And you'd think that you could make these little windows short, but Hadoop does not append lightly. And it doesn't handle great vats, at least stock Hadoop doesn't, great vats of files. And so there's a limit to how short you can make those intervals. And typically an hour or a day is congenial to Hadoop. 5 minutes begins to be quite abusive. So we've got a problem. We've got a gap there. The red stuff is the gap. So let's use real-time, because we got real-time data, which is exactly what Storm does. We have a limited amount of state. The length of the red line is how much state we need. And so Storm does exactly the thing that Hadoop does not in this example. And so what we'd like to do is take that sad picture with the gap there, make Storm, make it green, and then provide at the presentation level a blended view of those two things. So here's a specific example. I'm just going to do something simple. It's going to be counting. And we're going to be counting things with labels as they come in. And they're going to come in either slowly or quickly. And I want aggregates, say, per second. Real-time cool graphs. Per minute, per day, per week, maybe per year, that sort of thing. Very large range of timescales in the same system. And within that large range of timescales, I want 2-second or less response under all normal circumstances. So on the annual sort of thing, I can't wait to the end of the year to get the totals for the year so far. And I can't have a window or a Storm timeout that's 1 year long to wait to replay the stuff for the 1 second, 1 minute totals. So I have this mismatch in scales within the single system. And of course, we want the yada, 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 failure tolerant, and so on. And in fact, we'd like some pretty strict failure tolerance even when things break in a modest way. A node goes down, a rat gets lost. We want 30 seconds, say, delay in the data. We don't want to lose the data. We just want to delay it a little bit. And the almost always refers to truly cataclysmic things, like the entire data center loses power. Well, we could have a long delay in that case. And we may lose some data that's coming in and we're not capturing. And that's what the almost always is. There's always an almost always. The essence of real time is to make promises and pretty much always keep them, but explain when you won't, what circumstances you won't, and why you won't in a reasonable way. So here's a design. So we got a search engine-ish or something producing queries. And just for completeness, let's log those off to the side into raw logs. And then we're going to have a counter bolt. Now I've drawn some of these arrows red. Those indicate high transaction volume sort of connections. And some of them are dashed blue lines. And those indicate the lower bandwidth sorts of things. And so what's going to happen is the counter bolt here is going to produce semi-aggregated results that it burps fairly frequently to the logger bolt, which is going to persist those immediately. So once those things go out, we can acknowledge everything that came in, because once it's out and persisted, we're safe. And then periodically, every hour or day, we'll do a snapshot and run a Hadoop job against that now static data while we continue to dribble data in from the logger bolt. And of course, I'm not showing the view side here, but we'll come to that in a little moment. And you can imagine already that something that looks at this and rolls up the semi-aggregated data and looks at that to get long-term aggregated data could provide a seamless view. So the counter in detail is going to take labels for input and short-term semi-aggregated counts. Now these are going to be duplicated because we're going to emit them more often than a year. And these are our primary state preservation mechanisms for failure tolerance. And so we're going to emit all non-zero counts once we reach a lot of query or things that have come through, or we reach a time limit of how long we want things to stay pending. And once we emit that, things are no longer pending. We've emitted it, we've passed on the responsibility, it's done. And the tuples then can be acknowledged when the counts are emitted. And there's a tiny probability of double counting if we emit them and we have not yet acknowledged them, consecutive lines of code. And I'm willing to take that. I'm not willing to take a sort of thing where all the counts go to zero when a node fails and they recover over a period of weeks. That's not good enough. But I am willing to take if a node dies at exactly the wrong line of code, we may have one count or 5 or 100 that are off by 1. And that I can live with. Again, it's a matter of making promises that have bounds that are realistic. So there's some counterintuitive aspects of the counter bolt here. One is that counts are emitted for the same label, the same time window, many times. If it's once per second, we're going to emit 80,000 of those per day for something that's coming in quite often. And so these are semi-aggregated, which works just like a combiner in Hadoop, and it compresses data if the counts are large enough. And we may want to extend that in some way in order to get those counts to be large enough. On the other hand, if the counts are not large enough, we probably don't have high transaction rates, so it may not matter. So this semi-aggregation is in fact a feature, and we can acknowledge tuples within a second or so, and time windows can be much longer than the acknowledgement time. That's the key feature of that design. And we have no need, if we're going to have enough counts, to send the same tuple always to the same bolt. And that could speed some certain recovery scenarios, because if something dies here, we don't have to wait for a replacement for it. We can immediately send the tuple to somebody else. A little bit odd characteristics, but they are what give us these very nice properties of long time windows and short ACK times, which gives us then short recovery times for the storm framework. Now we have some design flexibility there. So for instance, the counter can persist a short-term transaction log. Instead of emitting it, it can leave a log there, and it can keep more data in memory if that log is available across the cluster, because then somebody else starting up could read that log and recover what partial state there is. And that could extend our flush windows quite a bit. 10 seconds, a minute, several minutes if we want to. Now, extending those flush windows limits our real-time response unless we directly probe the counterbolt, which adds complexity. It's usually not desirable. And the log is normally never read. It's only read under failure scenarios, so we have some very light duty as far as storing that's concerned. Now, there's some things we must not do. We can't accumulate an entire year in memory, because that presumes that we'll be there for the next year. We can't just assume that we will. Something's going to happen. I mean, you can view operations personnel as hardware failures in some sense. That's a nice decoupling. So they're allowed to just go do stuff, and shit happens to your program and you deal with it. Then they don't have to send warnings, they can operate much faster and so on. They don't particularly like being considered a hardware fault, but it's a profitable way to do it. But that means you can't assume these long-lasted processes. They'll last for a while, but they may not last forever. And so we have to persist the state somehow. This design persists at every second or so that's not a big deal. But we have to worry about if that state grows too large to handle without disk access, because if we touch the disk, that fancy speed argument's gone. And we can't persist the entire count table at once, because it'll take a while. We have to do it incrementally, as in a log. But here are the guarantees that we get. We have some bandwidth guarantees, no more than 100K outputs per second, or K tuples per 100,000 inputs, or K tuples per second. So assuming that the counts are large, we have a very large bandwidth decrease from the input to the output of the counterbolt. And on average, because it bounds at 100,000 anyway, it's about 1 tuple per second per label per bolt for this exercise. The persistence layer, though, has to give us some guarantees. And this is an important point. And this was what really makes the Hadoop integration hard. And that is this. We have to have a readable flush. Somebody has to be able to read our flushed data, or we have to be able to close the file, reopen it, and append some data. Neither of those is true in general in HDFS, which is what Hadoop is normally run on. The good news is that both are true for MapRFS. It's a real file system. And as an example, you have issues in Hadoop where closing a file, it may be 10 or more seconds before anybody else can see the file. That's the sort of issue that you're dealing with. And it's clearly just not suitable for real time. So the crux of this is that the storage and persistence layer has to be as real time as we would like to be. Or put the other way, we have to be willing to be as non-real time as the storage layer is. So if you pick a non-real time storage layer, you have to live with that. Or you pick a real-time storage layer, and then you can make guarantees. The system will fail in these ways. If a bolt fails, buffered tuples that were waiting in memory to be emitted will go unacknowledged. And after a timeout, short, usually 10 seconds or so, these tuples will be resent, recounted, probably by somebody else. And if the failure occurs after the persistence and before acking them, we'll get a double count on those for 1 second or so. If we have a storage layer failure, and those can occur regardless of how carefully we build things, most failures in a MapR storage layer are invisible. You don't see them because the spares take over before you know. But a few can result in a resynchronization time of a few seconds, very occasionally 10 seconds, and the catastrophic level delay is a full cluster restart set from 0 power back on. And that's 2 to 3 minutes for the complete cluster comes up, everybody figures out that they've booted and are in good shape again. So the logger could conceivably buffer that much data on a lot of systems, in fact. Although if the whole cluster goes down, chances are good the whole real-time system is down too, because we've probably lost the data center. So those are the failure scenarios that this has.